Welcome back. In this series of videos, I'm presenting some results on curves that are extremal for the extended endpoint map on subRiemannian Lie groups. Previously, we obtained the normal equation and the abnormal equation. Now, I will take the derivative of these equations and obtain some further results. Let's recap what we have already saw in the case of subRiemannian Lie groups for those energy minimizing curves. So we are in the setting of having G, delta, and scalar product, a subRiemannian Lie group. We have fixed E1 to EM, where M is the rank of delta, an orthonormal frame, a basis for delta at 1. And then we saw that if gamma from 0, 1 into G is a length minimizing curve parameterized with constant speed, let me just say is length minimizing with constant speed, then it is energy minimizing. So the differential of the extended endpoint map is not surjective. And then we wrote that its control U, which is an element of L2, 0, 1, valued into delta at 1, satisfies at least one of the two following equations. What are the equations? So, number 1, we called it normal equation. It was that there exists lambda in G star such that G is the real algebra of the group G, such that U is equal to the sum for I from 1 to M of lambda add gamma EI. Maybe in the previous video I wrote it as gamma dot, but this is what is U. U is just the left invariant, so the pullback at the identity of gamma. Maybe I'll write it, recall it here. So gamma dot is the differential of the left translation by gamma applied to U. Okay, so this was the normal equation. What is the abnormal, and then there is also the abnormal equation. Don't do the mistake of thinking that they are exclusive. A curve, okay, for a given lambda, one of the equation at most is true, but a curve might admit, might satisfy the normal equation for some lambda, and another, and the abnormal equation for another lambda. So, if there exists some lambda for which lambda add gamma EI is equal to 0, and this is a sequence, this is a system of equation. Okay, for any I, there is one equation. Okay, now of course, you see, the same lambda cannot be giving both normal and abnormal equation, because you see this element here is the same that is written here, right? So if we're and for sure u is not a zero vector. Actually, it's a constant norm vector function, right? So the norm at every point is constant, it's the same, and it's non-zero because, okay, let's say that the curve is not a constant curve. Okay, all right. So now, seeing that there is still the same function here, let's see what happens if we differentiate this function. So let's differentiate the function t goes to lambda. We can forget about it because it's going to be linear. So just let's differentiate this function as a function of t. And when v is instead is fixed, okay? So with v, say in the Lie algebra. Okay. Now, in the lecture note, there is the calculation of this derivative for general groups, but I will do it a little bit different. I will do it for linear groups. So d over dt of add gamma t applied to v. Let's write it for linear groups. Okay. So for linear groups, what we get, so this is d over dt, so the adjoint becomes just the conjugation, gamma t v gamma t minus 1. And now we want to take the derivative of each term. Okay. Now, what is the derivative of the inverse of a matrix that is depending on time? Okay, so we would be tempted to write this as equal gamma dot v gamma minus 1 plus gamma v, and now it's the derivative, so it's minus gamma minus 2 times gamma dot. Is this true? The derivative satisfies this equation? Actually, it's not correct. Let's do it here. So how do we calculate the derivative of the inverse of a curve? Okay, let's start with the fact that if you have gamma of, depending on t, times the inverse, then I have this multiplication is equal to the identity. Okay, let's take the derivative from here, d over dt. I have therefore 0 equal gamma dot times gamma minus 1 plus gamma, and then the derivative d over dt of gamma minus 1. And this is what I would like to calculate, right? But now from this equation, I have it. Now this is, what do I get is that d over dt of gamma minus 1, this is equal to, okay, bring on the other side, I have minus, I have to multiply on the left by gamma, so I have gamma minus 1, gamma dot, gamma minus 1. And this is the correct formula from this, okay? So let's make it, move it a little bit. So now this is wrong. This is wrong. Let's fix it. Okay. With the formula that's at the bottom. So now we have that this is gamma minus 1. Okay, there's a minus gamma dot gamma minus 1. Okay, so let's write it better. So this is okay, I will do all at once because now I remember the fact that gamma dot is the left translation of the control. But now remember we are in a linear group, so the left translation is just the multiplication. The differential is equal to the left translation. So this is the formula for the control. So I also use this formula. Okay, so at the beginning I have gamma u for this part here, then v gamma minus 1 plus, no, there was a minus, so it's minus gamma v gamma minus 1, and then I put gamma u gamma minus 1. Okay, now here is this simplification, and you see that everything is multiplied on the left by gamma and on the right by gamma minus 1. So what do I have is equal to gamma uv minus vu gamma minus 1. And I can write this as the adjoint by gamma of the bracket between u and v. Actually, this formula, as I wrote it, is true for every Lie group. But we just did the proof in the case of linear groups. Okay, so now we can differentiate these functions. Okay, so let's go back to our normal and abnormal equations. Okay, so for lambda in G star, say lambda different than 0, we have the normal equation. This was giving us u equal sum lambda add gamma ei times ei. And therefore, if I take the derivative, I have sum lambda add gamma u bracket ei. Instead, the abnormal equation, we had lambda of add gamma ei equal to 0 for all I. I take the derivative and I get lambda add gamma u ei equal to 0. Okay. Now, let's try to deduce some formulas, some consequence in some special cases. For example, what happens if we take now groups of rank, subRiemannian groups of rank 2? Maybe I should say the distributions of rank 2. Distribution of rank 2. What does it mean? This means that, for example, it means that u, so m, so here there was a sum from 1 to m, right? It means we have only m vector in m equal to 2, we have 2 vectors, so u is u1 e1 plus u2 e2. Now let's give a name to the bracket of u1 and u2. Let's call it e1 2. This is just definition. It's the bracket of u1 and u2. Now, what is therefore the bracket between u and e1? I have to calculate this kind of brackets, okay? So between u and e1, so this goes away. Now we have e2, e1, so it's minus e1, e2 times u2. So it's minus u2, e1, 2. And the bracket between u and e2, this is simply is u1, e1, 2. Okay, so now let's copy our normal and abnormal equations and let's see how we simplify in this case. Okay, good. So let's remove this. Okay, these are the normal and abnormal equation derived. We did the derivative of them. Okay. So now in the normal equation, what do we deduce? Let's see. So we can write it for rank 2 as equal, so u dot equal, so it's lambda add gamma. So both of them they're going to have e1, 2, and then we are going to have minus u2 e1, and then plus u1, e1 e2. Okay, this is for the normal equation. Abnormal equation. So this is simply telling us that we have minus u2 lambda add gamma e1, 2 equal to 0, and also e1 lambda add gamma e1, 2 equal to 0. Now remember, these vectors, these numbers are not both at the same time 0, right? Because recall that the norm of u, which is u1, u2, the norm of u1, u2 is the constant speed, non-zero speed. And therefore, if you have a curve with an abnormal curve, with constant speed, then what we have is the necessary, this has to be 0. Then lambda add gamma e1, 2 is equal to 0. This condition, which is true in a broader generality, is called go condition. Okay, now we can really conclude a corollary. So if you have G delta, the scalar product, is a subRiemannian group with dimension 3, topological dimension 3 as a manifold, and rank, the delta has rank 2, then no constant speed geodesic is abnormal. And hence, well, when we will prove that, hence that all of them, all these curves are normal and smooth. So in particular, we are saying that if you have one such group, subRiemannian group of topological dimension 3 and rank 2, then all the length minimizing curves, when parameterized by arc length, then they are smooth. Okay, what is the proof? The proof is, okay, let's consider gamma a constant speed geodesic. say with control to U, let's say up to left translation, we can assume that also the initial point is 1. So then we have as the image of a control. Now, the fact that we have rank delta equal to 2 and the dimension of G is equal to 3, then what we have is that, okay, we have E1, E2, an orthonormal frame, an orthonormal basis for delta 1, and their bracket have to be bracket generating, so this is one more bracket, completes the basis. So if I write E1, E2, E1, 2, this is a basis of the Lie algebra. Okay, now let's say by contradiction, assume gamma abnormal. So therefore exists lambda, a covector different than 0, with lambda is different than 0. And we have the abnormal equation, E1 and the one for E2, and the derived equation E1, 2. And all these three are equal to 0. Now, what happens now, what happens now if we take the equations at time 0, where gamma is the identity? What we get is that lambda, remember, so if now this is the identity, so the identity of the group, then the adjoint is the identity map. So we have lambda of E1 equal lambda of E2 equal lambda of E3, E1, 2 equal to 0. But therefore lambda is 0 on a basis. It has to be 0. This is a contradiction which concludes the proof of this corollary. Okay, now this was what I wanted to say for the abnormal case. Let's go back to the normal case. I want to tell you something more. So back to the normal case and in rank 2. Okay, so we know that there exists lambda covector such that U dot is equal to lambda add gamma E1, 2 times minus U1, E1 plus U1, E2. So this was what we get taking the derivative of the normal equation in rank 2. Okay. Now, let me introduce a curve sigma, defined on 0, 1, valued in R2. So this should be the planar curve with derivative equal to U. I'm saying, or let's say sigma 1, sigma 2 equal U1, U2. We call this curve, we call sigma the horizontal projection of gamma. Okay, so now we have this curve associated to gamma and to U. Now, what we have of this curve? So sigma dot, say this is U. So U is the tangent, okay? But now we have an equation for the derivative of the tangent. So for the second derivative of sigma dot dot, we know, so this is u dot, satisfies the equation lambda add gamma e12 times e1 u1 let us say, maybe here I did some mistake. Yes, so this should be u2 u2, okay, u2 e1 plus u1 e2. Okay, good. Now remember, like, the curves are smooth, so we could consider all these derivatives. Okay, so but now we have the first derivative and the second derivative of a planar curve. We can associate a quantity, that is the oriented curvature. So the curvature of a planar curve is K. So this is not the definition, this is one formula. I hope that you saw in your study at some point the curvature of a planar curve. And this is a formula when the curve is not parameterized by arc length, and which is this following: sigma 2 prime, sigma double prime 1 divided by the norm of sigma prime to the third. Okay, so take this for granted. Now I'm going to replace sigma prime and sigma double prime. So sigma prime, this is just u, right? We know that this is u1. Now, the second component of the second derivative, we get it from here. So it's the second component of this vector. Okay, so this is just a real number. The second component is exactly then this is exactly u1 multiplied by this number. Okay, so since both component, the second component and the first component will be multiplied by this, I will put this in evidence. Okay, but okay, I have u1 u2 dot minus u2 u1 dot divided by norm of u to the third. Now the equation before, we have lambda add gamma e12, and then you have u1 for e2 dot, we had u1, and then there was a change of sign, u2 u2. Okay, and this object here is the norm square of u. Okay, let's not forget the denominator. Okay, so what we have lambda add gamma e12 divided by norm of u. This equation is called the curvature equation for normal curves. Okay, and sometimes to calculate the normal curves, it's easier to calculate the curvature of them, of their horizontal projection. As a very simple example of subRiemannian Lie group, I will discuss now the Heisenberg group, which has already been discussed at the beginning of this course. But now we'll see that with the curvature equation, we have very quick proof of the set of geodesics. Okay? So let me quickly recall you what is the Heisenberg group. So, so let G be the simply connected Lie group with Lie algebra, with three-dimensional Lie algebra, spanned by three vectors, by E1, E2, and E3, such that E3 is the bracket of E1 and E2. So it's the one that we before called E12. And instead, E3 commutes with all the others. Okay, so this defines the algebra, and there exists a unique group to this problem. Okay, very good. So now, in the curvature equation, we had the term curvature equation. We had the term um, add was the gamma of E12. Okay, remember, so we can write gamma in exponential coordinates. So let's x of log of gamma by E12. And now we apply the property that is linking capital add and small add being the differential of capital add. So this is the matrix exponential E to apply to add of log gamma apply to E12. But now the exponential is the identity is, is given by the identity plus the matrix add log gamma plus the matrix square divided by 2 and so on. Apply to E1. But now look at this. E12, which is E3, it's in the center of the algebra, namely the bracket with everything is 0. So no matter what is log gamma, the bracket between this little r, remember, is the bracket. So the bracket between log gamma and E12 is 0. So it means that all these terms applied to E12 will be 0. So what we learn is that in the case of the Heisenberg group, this is just E12. Okay, so let's write the equation, the curvature equation for the Heisenberg. So the curvature equation for the Heisenberg group, or in the Heisenberg group, in the Heisenberg group is, so it was the curvature of the horizontal projection equal to lambda at gamma E12 divided by the norm of the control. Okay, so this was the curvature of horizontal projection. And we saw that this is equal to this lambda of E12 and this divided by the control. And remember, this control is constant because the speed is constant. Okay, so what we understand is that the conclusion is that the horizontal projection of geodesics parameterized by multiple of arc length, and so parameterized by arc length, are have constant curvature, and the planar curve with constant curvature are circles or lines. So are pieces of circles or pieces of lines. So this is a very quick proof of the formulas for the geodesics in the Heisenberg. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.